In this video, I'm going to discuss about the truncation errors for various numerical integration methods. And our focus is what does the truncation errors tell us? We are not looking into how to calculate the truncation error because it is too complicated to do so. Therefore, our focus will be looking at the interpretation of these equations. Okay. Now, when we try to study what does the truncation errors tells us, we can observe that for different methods, trapezoidal rule, Simpson's one-third rule, and Simpson's 3/8 rule, all the truncation errors actually consist of multiplication of three terms. We have a constant term multiplied by the derivative term and multiplied by the step size term. So these are the three things that we can use to interpret what does the truncation error tell us. Okay, what kind of information that the truncation errors will reveal? So first, we are going to look at this question. When does the numerical integration method gives zero error? Okay, that means that when the truncation error is equals to zero. If the error is zero, in other words, the best fit line that we use to approximate the function to be integrated should be equals. If you look at the three small diagram at the bottom of the slide, so we can see the first diagram is the trapezoidal rule. The straight line is used to approximate the function to be integrated, which is not so accurate. As for Simpson's one-third rule, a quadratic line is used to approximate the function to be integrated. And the third diagram shows that the Simpson's 3/8 rule uses the third order polynomial to approximate the function to be integrated. So if the approximated best fit line is perfectly matching the function to be integrated, then the truncation error will be exactly zero. So how do we know that mathematically? If you look at it mathematically, it helps us to remember better how do we explain the truncation error for different numerical integration methods. Okay, so if the truncation error has to be equal to zero, looking at these three terms, you can see that as I have highlighted, only the derivative term is possible to be equal to zero. The constant term are small values because it's 1 over 12, 1 over 90, 3 over 80, but it will not be zero for sure. As well as the step size. Step size is the width of a segment. You cannot have zero width. There is no such thing as no segment. You must have a very small step size at least. So step size can never be zero as well. Therefore, we can tell from this understanding that only the derivative can be equals to zero. So we can also see that trapezoidal rule uses the second order derivative to calculate the truncation error. Simpson's rules, whether it's Simpson's one-third or Simpson's 3/8, uses the fourth order derivative to calculate the truncation error. So how do we make use of this to determine when does the numerical integration method gives zero error? When we are considering trapezoidal rule, we will be looking at this general form of the numerical integration. So the derivative means is the derivative of fx. Okay, is a derivative of the function to be integrated. So let's look at an example. If the fx is ax plus b, for trapezoidal rule, if we differentiate two times, first time we will get only the constant a, okay, because the constant b disappeared and ax becomes a only. So if we differentiate the constant a again, the second order derivative will be equal to zero. So now we can see from here that if the second order derivative is equal to zero, that means this, when we multiply these three terms, the truncation error will also be equals to zero. So in this simple calculation over here, it shows us that if we use trapezoidal rule, it is able to approximate the function to be integrated perfectly if the function to be integrated is a straight line. Okay, so we use the same concept to apply to Simpson's rules. Okay, let's look at this third order polynomial as an example, which means if the function to be integrated is a third order polynomial, as we differentiate first time, let's look at the left hand side only first, we will get 3ax squared. So the order of the polynomial reduced by 1 when we differentiate one time. And in the second line, the second order derivative further reduce the order by 1. So from order 3 becomes order 2, now becomes order 1. So when we look at the right hand side, the third order derivative will become 6a. Okay, and the fourth order derivative will be equal to 0. So we can see from here that if the function to be integrated is order 3 polynomial, then Simpson's rule will be able to perfectly approximate the function to be integrated. So we can also further extend this concept and see that if it is lesser than order 3, even before we reach the fourth order derivative, the derivative already becomes 0. So the Simpson's rule is also able to approximate any function that is lower than order 3 polynomial. So that is how we can reveal what does the truncation error equation tell us in terms of the derivative. Okay, second, we can also make use of this set of truncation errors equation to reveal why Simpson's rules are more accurate than the trapezoidal rules. So in this case, we are also focused on the same integration, the same function to be integrated so that we can do the comparison, and we are looking at only the single application. So we have seen just now that the truncation error equation has 3 terms. So let's investigate this situation based on every single term in the equation. First, we will look at the constant term. It is not too significant as compared to the derivative and step size term. In the constant column, you can see that 1 over 12 is a value of 0.0833. 1 over 90 is 0.0111. 3 over 80 is 0.0375. Even though the constant values are different, but they are all very small value. They are all 0.0 something. So this tells us that actually the constant value, of course, makes some difference in terms of how big is the truncation error, but we will see in the next two slides, it will not be as significant as the impact of the derivative term as well as the step size term. So that's why the conclusion here is that there is no point to look at the constant term. They are just not too significant as compared to the other two. Okay, next we are going to look at the derivative term, which is more significant. Why is it so? Okay, let's base on the same function to be integrated. For example, ax power 4 plus bx power 3 plus cx power 2 plus dx plus e. So if we investigate based on the derivative term, we can see that trapezoidal rule, the error is depends on the second order derivative, and the Simpson's rule, the error is depends on the fourth order derivative. So we can differentiate the function to be integrated 4 times. Okay, we will get these 4 derivatives. So we will focus on looking at the second order derivative as well as the fourth order derivative. So we can see that the second order derivative is actually a order 2 polynomial, and the fourth order is just a constant. So it is very obvious that second order derivative will have a higher power of x compared to the fourth order derivative. Therefore, we know that if we substitute the value of x into the second order and the fourth order derivative, the numerical value for the second order derivative is definitely higher than the fourth order derivative. Okay, so if this has a higher value, as we multiply, we know that the truncation error will also be larger. So this is what we can tell from the truncation error based on the derivative terms. Next, we are going to look at the step size term. Okay, so same thing, because we are comparing the trapezoidal and Simpson's rule, we are still going to base on the same function to be integrated and single application of these 3 methods. So looking at the step size, it will be more significant. Let's look at why is it so. Now, please take note of one thing. It is reasonable that the step size are very small because we are dealing with numerical methods which we can use computer to help us to do a lot of calculation very quickly. Therefore, it is reasonable to use a very small value for the step size. And no point to use a big value because we know that the smaller value the step size is, the more accurate is the result. So why not we use a very small value for the step size? Therefore, usually the step size will be less than 1. So that's why our analysis will base on this concept here. Okay, so let's just take a value that is less than 1. For example, if the step size is 0.5. Okay, and we investigate what is the impact of the step size. If step size is 0.5, we can see that for trapezoidal rule, the error will depend on h power 3, which is 0.125. But the Simpson's rules both depends on h power 5, which is 0.03125. So 0.1 compared to 0.03, we can see that it is definitely the Simpson's rule will lead to a much smaller truncation error. So this is how we can make use of a simple calculation like this to remind us what is the impact of the step size term. Next, we can also make use of the truncation errors equation to reveal what happens to the error when we change the step size. So this situation is when you see this notation where we say that the truncation error is a function of the step size, because now we are going to focus on investigating only the step size, or only the step size term to be exact. Okay, therefore, the Simpson's rule will be function of h power 5. Okay, based on this equation, truncation error is the function of h power 3. So what happens if we change the step size? So we are going to look at this case where the ETH indicating the original step size. In the second line, we are going to investigate that if ET 0.5h is equals to what? That means if we reduce the step size by half, that's why I use the notation 0.5h. So how does it impact the value for the error? How much the error will reduce? Okay, so we can actually calculate the result without memorizing anything. So we start with ET 0.5h. So that means instead of h power 3, it is now h over 2 power 3. This will become h power 3 divided by 8. Since divided by 8 is a constant term, we can take it out of the O function. We will have 1 over 8 multiplied by OH3. And we can see here, OH3 is exactly the truncation error for ETH. So therefore, we have the conclusion that when we halve the step size, the truncation error will become 1/8 of the original. You can also use the same approach to investigate what if I divide the step size by 3, divide the step size by 5, or what, to investigate how will it impact the truncation error, how much the truncation error will be reduced. If you find it a bit hard to look at it based on this function O, which is a function of the step size, you can also just perform this calculation based on the original truncation error equation. So I will just quickly show you how to do that. Now, the original equation, as in, we look at the complete equation. Okay, ETH is equals to 1 over 12 multiplied by second order derivative multiplied by h power 3. Okay, so if I halve the step size, ET 0.5h will equals to the step size instead of h power 3, now it becomes h over 2 power 3. And if I expand this equation, I will then get the step size terms become h power 3 divided by 8. So compare this portion of the equation, we can see that it is exactly the same as the original truncation error equation when the step size is h. So therefore, we can substitute ETH into this equation, and we get ET 0.5h is equals to 1 over 8 multiplied by ETH. So this way, you can also calculate what is the changes to the truncation error when you make changes to the step size. Okay, so in this video, I have discussed how do we actually make use of the truncation error to perform different comparison or review different situation when we apply the numerical integration methods. So in this video, I have shown different way of making use of the truncation error equation to help us to compare different numerical integration method. In this kind of analysis, we focus on what does the truncation error equation tells us instead of calculate what is the truncation error.